Last time we discussed how to derive the wave equation from the Maxwell equations in vacuum. Now today we generalize that to linear medium and see how the wave propagates across the boundaries of two different medium. So the Maxwell equations for general medium is shown here, derived from the chapter 7. Now if the medium is homogeneous and linear, then the equations reduce to the equations over here. So they are exactly identical to the Maxwell's equations in vacuum, except that you need to replace the constant mu naught epsilon naught by mu and epsilon. So you see that in the medium, the wave equation also applies, and the velocity for that wave of propagation is slightly different, which is not the speed of light, but the speed of light divided by a index of refraction. And this index of refraction is simply being defined by the ratio of the speed of propagation to the speed of light. Now, this index of refraction is typically larger than 1, and since mu is very close to mu naught, then the index of refraction is typically defined by only the electric susceptibility, which is square root of the electric susceptibility. But one thing I want to mention is that this, even though the index of refraction is a constant, it can still depend on the frequency of the light. And keep in mind that we actually calculated the susceptibility in chapter 3 in the electric field in media, but at that time we were discussing the susceptibility for static electric field, and this is actually need to be take care in the sense that the electric field, if it's oscillating in a fast frequency, the AC susceptibility is different from the static susceptibility. So for example, for the DC susceptibility, the N index of refraction could be 8 for water, or for glass, and the N can actually only be around on the water of 1, say, for the water. So the susceptibility is could depend on the frequency hugely, and if you are familiar with Newton's triangle, that is actually to use the fact that the susceptibility actually depends on the frequency to separate out the rainbow of light. Now, from the Maxwell equations, we can also get the energy density of light in media analogous to the light propagated in vacuum. Instead of epsilon naught and mu naught, we have epsilon and mu here. And for the Poynting vector, which represents the average of the Poynting vector, represents the intensity of the light. And now for the Poynting vector, it's E cross B divided by this mu. So we have to be careful that for the B field, it is 1 over V times the amplitude of the E instead of 1 over C. So now if we calculate the intensity of the light, that should be 1/2 of epsilon V times E naught squared. Now we try to see how waves cross this media. and that is we simply apply the boundary conditions and try to match that with our solutions. So for the boundary condition is exactly what we get from chapter 7, and as for simplicity, we start with a normal incidence. So we can write down the incident light here. That is, we first can pick the polarization of the electric field. We can actually, so the polarization vector of the electric field must be perpendicular to the B field. So it doesn't matter which direction it points, and we can define the polarization vector as along the x-axis. Now, after we define that, then the b-axis must be along the y direction, because E cross B gives us the pointing vector direction, which is along the z direction v here. So likewise, we can get the transmitted light. The electric field must be, we can assume that is along the x direction, and then the B field it must be along the y direction, and for this reflected wave, we have to be careful that the B field actually takes an additional minus sign, and that is because the pointing vector of the B field, of the reflected light is coming in the opposite direction of the pointing vector for the uppercase. So here we have to let x cross minus y to be along the direction of minus z. So the b has to be along the minus y direction. Now we can see that in this normal incidence case, the electric field is always being parallel to this plane, to this interface or this boundary. So this first equation actually automatically satisfies, and likewise the electric field is also parallel to this plane of boundary. So the third equation is also automatically satisfied. So we only have two boundary conditions, and we have here 1, 2, 3 different variables. So we can express this reflected amplitude and transmitted amplitude in terms of the incident amplitude. Now, the first equation gives us a relationship between the E. The fourth one gives us a relationship between the B field. Now we can re-express the relationship of B field in terms of E fields. We can simply combine these two and solve for this ER and ET. So the final result is over here. And here this beta is simply a convenient definition of this mu1 v1 over mu2 v2. So we see that since the mu here is almost close to mu naught, so we can actually set the mu1 equal to mu2, and in this case we see that it's very similar to what we have calculated before for this waves on a string. Indeed, they are actually identical to each other if we make the approximation of mu being the same. Well, then everything that we discussed for the motion of this string can be applied here. So for example, here you see that this reflected light can take a minus sign if V2 is less than V1. So in that case, then when the light is being reflected, we must pay attention that it has to add additional 180 degrees phase. Now we can looking at the amplitude here, we see that if we can re-express the speed of light in terms of the index of refraction, the final result is shown here. From the electric field, we can go one step forward and calculate the intensity. Now, once we get the intensity ratio of the intensities, we can then calculate the quantity called refraction coefficient or transmission coefficient. The refraction coefficient is simply reflecting what percentage of power is being reflected, and the transmission coefficient is simply calculating what percentage of power is being transmitted. Now, for the reflection power, for the reflection coefficient, it depends only on this E square, but for this transmission coefficient, because epsilon 1 V1 and epsilon 2 V2 could be slightly different, so we need to include an additional factor. But once we get the final expressions for this transmission and the coefficient, reflection coefficient, because of the conservation of the energy, we can double check that indeed they add up to 1. So what I just talked about is the normal incidence, which is a very special case where the light simply hits the boundary or hits the interface exactly at 90 degrees. And for more general case, we have to let the light the incident at arbitrary angle. So here let's take a look at this case where the light is coming at an angle where there is an angle of incidence, and then it can be reflected where there is an angle of refraction, and it can also be transmitted, so there is an angle of transmission. So I think you all have learned this in optics, right? Okay, so yeah, in optics, you know that there are several famous laws. So one law is being that all three vectors must form a plane, right? And then the reflected angle must be equal to the the incidence angle, and there is the additional famous law called Snell's law. So it can relate the incidence of angle to this transmitted angle by a sine function, and also the refractional index n1 and n2. Okay, but you haven't learned how to derive these equations, right? Okay, so now we will try to actually derive how these equations are obtained using the Maxwell's equations. So now if we write down the general solutions, then the general solutions is similar to what we wrote down for this for the normal incidence case. So except that for the normal incidence case, the result is relatively simple because the angle relations are simplified because of this normal incidence. Now you can see that if we somehow have an angle of the incidence here for this for the incoming incident light, then if we define a certain polarization vector for the electric field, then the magnetic field will take a k the propagation vector cross this electric field vector. So that's it, because it must the pointing vector must be along the vector of the propagation. So this actually introduced a annoying cross product here. So if you think carefully how this how the polarization vector E behaves might change your result. So say that the polarization is out of this surface. So say the polarization is out of the screen, and for the E field, then the K cross E gives the B field that is actually in plane, that's in the direction over there. And now consider the case where this E field is actually inside of this plane. So let's say that the E field is say perpendicular to the K, but inside of the screen. Now if we do a cross product, the K cross I give you a B field that is actually going out of the screen. So these two cases might actually be different, because now you can see that here for the electric field for this case where, sorry, I should actually specify. So this is the direction of the E, this is the direction of the B. So you see that for the E field that is inside into the screen, this E field is always parallel to this surface of this interface. But for the B field, we not only it has a parallel component, which is the component over here, it also has the additional perpendicular component. So the boundary conditions for the B field here is slightly more complicated than the E field. And similarly, for the case over here, the boundary condition for the E field is slightly more complicated than the boundary condition for the B field. So we have to discuss these two cases separately. Okay, so other than that, however, in the expression, the general expression for these two cases are also exactly the same as here. So here the equations doesn't distinguish how the wave actually propagates yet. So now let's actually not try to worry about the details of these two different cases here, but look at the general case, where here we are only looking at the general solution over here. So now for the boundary condition to satisfy, um, for one, we have to make sure that the frequencies of these solutions must be exactly equal to each other. So you can sort of imagine that if I incident one specific frequency in time, the reflected frequencies and the transmitted frequencies, or all of these omegas, has to be the single same number. So if it's not, then if you propagate in time, the relations actually cannot satisfy. So that is actually similar to the normal incidence case, or similar to the waves traveling on a string. So this one already sets some conditions on this wave vectors ki and kr, because this k vectors times the speed of the propagation equals to the frequency. So the speed of propagation is determined by this 1 over n1. Now, if we write down the solutions, the solutions then must be can be expressed by something like this. So the at the plane of the boundary, which is z equals 0, then even though we are not sure what should be the components coefficient in front, but what's on the exponent must be written down like this, because this is simply writing down this here the omega is the exact same frequency. Now if we even though we haven't done plug in all these initial conditions, we haven't plugged in this yet, we are sure that the final expression should be looking like this. So which means that both for the perpendicular polarization or for this parallel in the plane polarization, what you obtain finally will be in the form like this. So now if we but what I claim here is that if you simply look at this expression here, it's actually already tell you a lot of things, which is general to many propagation of waves. That's not only to the propagation wave of light, but also to the wave of say if you put a ripple on this on the surface of water, then the waves on top of the water actually will be guided by the same expressions. So it's the how the water waves transmit across some boundaries will exactly be the same expression over here. So for this kind of general expressions, we can actually more explicitly write down the spatial terms. So in the spatial terms, these three should be equal to each other, implies that the at z equals to exactly 0, and at any moment, these three must be equal to each other. So we have so you see that if these three terms are not exactly the same to each other, then imagine that if you satisfy a plus b. So now let's try to set this as a plus b. So if you at one point you find you magically find a plus b equals c, and then if you slightly shift your position at the plane of this of the plane of the boundary, then this equation might not be satisfied because this can introduce slightly different phase. So the condition for this solution to be always satisfied at the boundary of z equals 0 means that um, this terms must be always a constant across all the boundaries as for any. So for specifically at z equals 0 and for any x and y. So we have to so this is this has to be satisfied. Now if we write down the components explicitly, then this is simply the r vector is simply the x, y, z, and ki has the component of ki along the x, along y, along z. But here for we are interested at the plane where z equals 0, so we only write down the components involving x and y, and then this is the expression for by explicitly writing down all the components. Now for this expression to hold, all the components also needs to be hold, because this expression must again be satisfied by all the x's and all the y's, because here x and y can actually vary, and now you have to equate this kix to krx and kiy to this kry, and the same is for the transmitted light. So then from this we can already derive all the relations, all these laws from this your classical or this geometrical optics. So the first law in the classical or geometrical optics is this, that the incident, the reflected, and the transmitted waves actually form a plane, and here you can see that because here you have to satisfy the boundary conditions. If the boundary condition is satisfied, then these two expressions has to be satisfied, which means that if you translate, if you look at how this kix translates. Translates back to this picture. So let me try to. So and I just redraw the picture previously, and so here, um, because all this y component, because all this geometric component has to be each equal to each other, then it means that if we project that in the x component and in the y component and in the z component, um, so if we apply that in the hmm? So sorry for the first row. If we let the k to be in this xz plane, so here we only draw the plane of xz, and if we let the incident k to be in the xz plane, then because this ky equals to exactly incident equals to exactly 0, then all this reflected and transmitted y component should be exactly 0. So this is what suggests that the transmitted and transmitted and the reflected light should be all in the xz plane, which is the plane of the incidence, or the plane of this normal vector and the boundary. So that the first law is easy, and then the second law is to derive the law of the reflection. So again, we based on these two expressions. So if we check the z component, so we have this here for the ki along this z component must be equals to the to this kr along the z component. Then because the k for the k and the incident k and the reflected k must share the exact same um, amplitude, which means that the sign of the input and the sign of this reflected must be exactly equal to each other, which means theta I must be equal to theta r, which gives you the law of this reflection. Now, the third law is the law of the refraction. That is how to relate this transmitted angle with the incident angle. So the law of the transmission can also be derived by simply inspecting at all these components of the k, and so because now you can see that the along the z-axis they must be equal. Sorry, along the x-axis they must. Sorry, I should have said along the x-axis. So along the x-axis, the k must equal to each other. So this k k incident times the sign incident equals to the k transmitted by times the sign transmitted. But remember that the k vectors across a boundary can be slightly different, and they differ by the factor of nr over ni, because of the k times v equals to the omega, where the omega has to be a fixed, and the v can the speed of propagation can be different for different media. So then, if we from this expression we can derive the third law, which is the Snell's law, that the sine of this theta transmitted light over the sine of the incident light equals to n1 over n2. So from the Snell's law, we know that there is an angle of the total reflection depending on this incident media of n. But you see that all our derivation of this geometrical optics only involves by equating these exponential factors. We haven't actually derived the how the coefficient in front should be equal to each other, and we already obtained quite a bit, lot of information. Actually, all the information that we needed for this geometrical optics. So even though we haven't finished our calculation yet, so the information that we learn by simply equating all this, by equating these exponential factors, we obtain a lot. And now we actually want to continue the calculation. So which means we really have to apply all the boundary conditions and make sure that all these factors actually add up correctly. To do that, we have to just as what I discussed earlier, that we really need to specify what is the polarization of the light. So here, if you still remember in the previous lectures, I discussed that the polarization is can be in plane or can be an out of plane polarization. So for the in plane, I claim here as the parallel polarization. So what I mean is that the incident light is in the xz plane, and however the B field can be pointing out of the screen. Now here are the for this case, in principle, it's actually similar to how we solve the equations for the normal incidence, except that there are more unknowns and more equations. So if you check, if you still remember, in the normal incidence we eliminated some expressions. So in the normal incidence, the E is only E parallel, whereas in this case, the E has both a parallel component and a perpendicular component. So the boundary conditions are more, and the unknowns are also more. So if you try to explicitly solve the problem, the boundary conditions can is listed over here. So, but I'm not going to exactly dig into how every step is being derived. So I just want to quickly go through um, how this is being approached and try to make sure that the number of the variables should be um, equal to the number of boundary conditions such that you can eliminate all these expressions into expressions such that the reflected they must be all the coefficients must be determined up until one proportionality factor. So you can try to apply first is the boundary conditions along the perpendicular direction for the E field. So this is simply write out explicitly what should the E field be in the perpendicular direction. So remember here, in the previous step, we've already fixed that the exponential factor should be remaining a constant. So right now, we simply need to look at the coefficient in front. So the equations 1 can be simplified to here, and the equation 2 actually doesn't give you any additional information because you see that the B field is across the screen, so the B field is always parallel to this plane of to this plane of interface, and so this doesn't give you anything. And this is the parallel direction of the E field. So E field can be parallel to this along the x direction. So here, equating the E field, you simply project out the E field for all these components. And similarly, we can do the calculation for the parallel direction of the B field. Now, 4 boundary conditions give us 3 equations. Now, in the previous calculations, we also have the law of the reflection and the refraction. So all these angles, the incident angle and the reflected angles are related to each other. So let's see. Now, if we plug in the relations of the incident angle and reflected angles, we can reduce this expression and the last expression to the expression over here. So and we also have additional equation 3, which gives us the expression over here. So in the end, we have 2 independent equations, and then from these 2 independent equations, we have 3 unknowns, just like before. So which is then from these 3 for these 3 unknowns with 2 independent equations, we can solve say the reflected and the transmitted in terms of the incident E field. Now we define, so the beta is the exact same definition as before, and somehow Griffiths also introduced additional definition of the alpha, which is the cosine function of the transmitted and the incident light. So in the so here by expressing the everything in terms of alpha and beta, it simplifies the expressions, but in other textbooks, such as in the textbooks of Jackson, which you might encounter later, you might find that they sometimes explicitly write out the N2 and the N1, and the expression here, if you expand out the cosines and the N1, N2, these are actually somewhat complicated equations. So so these equations are actually extremely powerful, and tells you much more other than the traditional geometrical optics. So if you solve, so if you plot all these solutions, you can actually see that the electric field, how the electric field, how the ratio of this electric field depends on your incident angle. So, but remember that this is specifically for the in-plane or the parallel polarization. So for this incident light, the transmitted E is always a decreasing function, and however, the reflected light actually is, even though it's a increasing function, the function is strange that it crosses a zero here. So I'm not sure if you have heard of this angle. It's called Brewster's angle. Okay, so I think this is something that's very different from the geometrical optics. So the claim is actually here. For this is a magic angle. So for this angle, if you incident polarize the light, where the light polarization is in plane or in parallel to the plane, then you actually expect that there won't be any reflected light. So all the light will be transmitted into the media. So this is not quite intuitive, right? So and I bet you haven't seen this kind of, or if you, I bet you are not not notice this phenomena in nature, because in nature we typically don't have polarized light. But if you do experiments using a laser, you might notice this clearly. But the another point is that we can actually make the use of the Brewster angle to make a polarized light. So which means that now, even though initially our polarization of the light can be arbitrary direction, but once we hit the light into the using this magic angle or the Brewster's angle, then for the transmitted, we know that for the transmitted light, it can be the in-plane propagation can transmit through the media, but the reflected light, that is guaranteed to not have the polarization of in-plane polarization. So this is one old way of producing polarized light from a normal distribution or random lights. But this also has limitations, because in this way you lose 50% of the light, and this is why this is not quite used nowadays. But this is indeed one of the first methods to create polarized light. And now if you do this experiment again using the polarized light, you can verify this the equations were here, and also this means that the Maxwell equations can be to extent checked in the boundaries of two medias. Now here, this is simply the plotting of the light intensity, so which is the squared of the E fields, and then at this point again the transmission coefficient reaches 1, and the reflection coefficient reaches 0, which is the magical angle here.